Booyakash. I'm not going to do that one. Never mind. Anyway, so this is episode 8 of my little Kim tutor thingy. And we're about halfway through the semester. And this is the second time I've done this because I hear people doing this on podcasts all the time. You record and then it happened to me because I haven't learned that stop broadcast is a different button than stop sharing the screen, even though one is a big red button, one is a little blue button. But anyway, we're halfway through. I didn't lose that much time. We're halfway through the semester. And most folks are into gas laws, and they got their second exam coming up. And general, that's general 1. And in general 2, most folks are starting to head through equilibrium, ice table stuff, and starting acid-base stuff, and they got their next exam coming up. So we're going to talk a little bit about that stuff. I've said stuff a lot, haven't I? Oh, well. So starting with general 1. Oh yeah, I forgot to say, special hello to all the bots from Russia that are visiting the show. I noticed I've actually got more Russian bots watching the show right now than people. And because what happened was I finally looked at the stats for this stuff, and all right, and I noticed Russia being like one of the top draws, and then I looked at one of the top visitors, direct, my site, whatever, and it said, oh yeah, such and such a blah 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 bullshit url.com. Oh, they're bots from Russia. So hello to our new robot overlords. But anyway, back to general 1. So at this point, people are starting to learn the gas laws. So we'll talk a little bit about that. And most Gen 1 classes, you're looking at usually 4 gas laws, maybe a 5th. The 3 historical gas laws, as I call them, because they're named after dead people. Boyles, Charles, and Avogadro. Sometimes I call them the 1-2 equations for obvious reasons. Some folks may learn a 4th equation named after a couple of guys named, actually, I think it's one guy named Gay-Lussac. The Gay-Lussac law, which relates pressure and temperature. But that some do, some don't. Most classes, they'll at least cover these 3 because those will lead into the ideal gas law, which is, some people call it a super law, because it takes all these other gas laws and puts them into one big equation. And the variables here, the letters are pretty self-explanatory. P is pressure, V is volume, T is temperature. N's a new one. That's going to be our symbol for moles. For quite a bit, this and other classes, as folks in General 2 can attest to. That's ugly. I like that better. There we go. And R is a constant, and the units of R vary depending on what equation you use it in. But in the ideal gas law, it's 0.08206 in units of atmosphere liter per mole Kelvin. So when you're first introduced to these equations, you see 2 main types of problems, 2 main types of scenarios where you use them. For the 1-2 equations, you usually see them in cases where you've got a gas under certain conditions, and if you change one condition, you can calculate another, usually by holding something else constant. So like here, for example, you got a gas at 400 milliliters at 20 and 25 degrees Celsius or centigrade. What will be the volume if you hike the temperature up to 200 degrees, holding the pressure constant? Have to hold the pressure constant because according to Boyle's law, that pressure can affect volume. So again, that's this typical setup. You got a gas under certain conditions, change one, find something else. And these sort of changey type problems, a non-scientific term, changey type problem, They usually involve one of our little 1-2 equations. Again, the historical ones named after dead people. So, oops, don't go there. In this case, we're talking about volume and temperature, so it looks like Charles's law would be a good candidate. And let's see. It doesn't matter what you label as 1s and 2s. Some people use I's and F's for initials and finals, but I use 1s and 2s. It doesn't matter what you call the 1s, what you call the 2s, as long as you keep your 1s and 2s together. So, for example, if you call volume 1 400 milliliters, the temperature that goes with that volume, you should call it T1. Don't call it T2 because that won't work. All right. We're looking for a volume at a temperature of 200 degrees. So yeah, it looks like we have 3 of the 4 variables in this equation. So we have everything we need to find V2. And even though we're kind of going from more unit conversion math to algebra type math, it's a simple type of solve for X algebra. So, which is pretty much the way it's going to be for most of General 1, if not all of it. The General 2 things get a little more involved as far as math prereqs go, which you'll see if you just wait around for the General 2 part of the show. But in this case, we got 3 of our 4, find the 4th. One thing about Charles's law, though, that's a little different from the other 2, and I guess this applies to Gay-Lussac as well, if you're using it, that, pressure and volume for these 1-2 equations can be any unit. It can be atmospheres, torr for pressure, any liter, milliliter, whatever for volume. But temperature has to be plugged in units of Kelvin. Because you're going to get 2 different answers if you plug in 25 and 200 than if you plug in 298 Kelvin or 473 Kelvin. All right, so we're going to calculate in Kelvin, mainly because, remember, Kelvin's an absolute scale, has an absolute 0, no negative numbers. So you can imagine a problem like this where if one of these temperatures was negative, negative 25 degrees C, the other was positive, you could end up with a negative volume, which isn't possible. So again, we calculate in Kelvin, mainly for that reason. So plugging everything in, 400 milliliters, 298 Kelvin, V2, and 473 Kelvin. So it's just basically solve for X algebra is all we're doing at this point. Starting to move away a little bit from unit conversions, not completely, as we talk about later in the chapter. But it's not that bad. Getting 3 variables, solve for X. And that will give us 635. Oh, and I did it, but I didn't talk about it. But notice the unit-wise, the temperature unit drops out. We're left with a unit of volume, which is good because we're looking for volume. So even though we're not doing unit conversion, or we're starting to move away from unit conversion math, even if you're doing the solve for X type of algebra, you still have to be mindful of units. So it's really important to just, when you're scratching this stuff out, take the extra 3 seconds to write these 4 letters. You'll be surprised how many points it'll save you. Trust me, there are plenty of times where I have seen a page and it's nothing but numbers and no units, and I think, oh, this isn't going to be good. And yeah, a lot of times they get it wrong, and they get it, and if they just put in the units, they probably would have caught some stuff, which actually we'll see that in the next problem. All right. So that's your basic setup for the 1-2 types of equations: Boyle's, Charles, Avogadro's, Gay-Lussac. Again, same setup. Typically the same setup. You know, you've got a gas under these conditions. You change one, find another. The ideal gas law, there's a few different ways we can use the ideal gas law. And we see some of those applications later on in the chapter. But initially, the way ideal gas law is just as an equation. You got 4 variables in this equation, plus your 1 constant. If you know 3 of them, you can find the 4th. So that's a typical problem. They give you a gas under 3 of the 4 conditions, and they ask you to find the 4th condition. Like in this case, you have 10 grams of carbon dioxide in a 750 milliliter container at 295 Kelvin. Find the pressure. So one thing to be careful of, though, is, again, be mindful of units. Because this, unlike the other equations that we showed, or I showed, you looked, this equation has a constant, and there are units associated with that constant. And so any of the things you plug into this equation, those other 4 variables, their units have to match the units in the gas constant. Pressure has to be in atmospheres, volume has to be in liters, amount in moles, temperature in Kelvin. So temperature or volume, or temperature is already in Kelvin. Volumes in milliliters, needed in liters. Most folks by this point know the little move the decimal over trick to give you 0.75 liters. If not, it's a chapter 1 conversion, which I'll skip just to save time. We're given the amount of carbon dioxide in grams. We need it in moles. But by this point in the semester, that should be old hat, if I'm saying that phrase correctly. What does that mean anyway, old hat? I don't know. No. But yeah. Converting using carbon dioxide's molar mass of, oops, I was trying to, the old hat thing stuck me and I just started wandering like an old man. Yep. Here we go. Oh no, here. 1 mole of CO2 for 44 grams. So yeah, using CO2's molar mass, we can convert that to 0.227 mole. So now we can plug everything in. You have 0.227 moles times your gas constant. And problems like this especially are where people start to get lazy with units. I don't know, there's a lot to write with that gas constant, but just take the extra 5 seconds to write it. Especially in a problem like this, because again, all the units have to drop out except the pressure unit because we're looking for a pressure. Kelvin drops out, or not. Whoops, I'm missing one. Oh no, V. I'm sorry. I'm still thinking about old hat. No, not really. I just screwed up. Actually, I was thinking about something I forgot to mention, but yeah, P equal nRT over V, dummy. So 0.75 or liters. There we go. So yeah, temperature drops out, the volume drops out. A lot of people screw up and plug in 10 grams, and if they, or they just plug in 10. If they actually plug in 10 grams, yeah, then they will see, oh yeah, gram, mole, that doesn't work. I got to convert to moles. So you always take the time to convert the units, or show the units, write the units, whatever. All right, so you plug that in, and that gives you a pressure of 7.33 atmospheres. So for these kind of gas law problems, a lot of it, like a lot of things in this course, is you do through practice. And you kind of get a feel for what type of problems you're running into. Like, again, the 1-2 equations, they usually have really common types of setup. Um, just using the ideal gas law as a straight equation has similar setup. Again, you have 3 of the 4 variables, find the 4th. And if you're not sure, you think you know which one you're doing, just do like I did earlier and just start checking things off. All right, we're looking for a pressure, we're given a volume, we're given the mass, we can convert to moles, we know R, we know T. Yep, we got everything we need to find P. So, but once through practice, again, you kind of get a feel for how the equations are, or how the questions are asked. I'm trying to make sure I hit the right button this time, and I did. But again, for the most part, they're just simple solve for x types of calculations. Actually, for all of them, the ones we talked about, you have 3 variables, and you find a 4th. One of them you have a constant, so you have to worry a little bit more about units. And that's pretty much it for the gas laws, at least for right now. There's more stuff to talk about in the gas chapter regarding the ideal gas law, but we'll talk about that after the break. For now, we'll move on to General 2, which is going to be dealing with the ICE method, which that's really the stoichiometry of General 2. Because once you start doing the ICE table, you do it in the next chapter and maybe the chapter after that. Maybe the chapter after that, depending on who's teaching you. So there are a couple different ways that you're going to use the ICE method for just the the intro to equilibrium chapter. There's 2 main ways, or 2 main types of calculations where you use the ICE table. And one of them involves approximation. But what I've noticed is that people will do the approximation thing when they don't have to, or they'll do the FOIL method in quadratics when they don't have to. And for those types of problems, if you go to my old Gen Chem Concepts website, tongue twister of a name, which is linked somewhere. My website, my YouTube channel is there somewhere. Or you just type ICE method, it'll pop up. I do a couple of videos covering that. So I'm going to do one example just to remind people of a case where you don't have to worry about approximation, or you don't have to worry about quadratics. And it's a problem that will often look something like this. Not this. This. Although the other ICE problems look like this too. I shouldn't have said that. But let's look at this example. I try to hide the blue dots when I do this. I forgot to, or squiggly lines. So a typical equilibrium ICE table problem, it says, find the concentrations of equilibrium when you start with this much of something. So they tell you what you're starting with. You're looking for equilibrium. Remember what the letters of ICE stand for. I is the initial concentrations, C is the change in concentration, E is the equilibrium concentrations. So again, you're looking for concentrations at equilibrium, and you're starting, or you initially have these concentrations. So again, most of these problems, with practice, you kind of get a feel for what type of problem you're running into, especially with ICE table problems, especially the equilibrium chapter. All right. So you have to set up an ICE table. So your initial concentrations are usually given to you in the problem. All right. So we initially have 4 molar concentrations of each reactant. They don't say anything about the product, so we assume we're not starting with any product. So if this is going to reach equilibrium, it's going to have to shift to the product side. We got to shift to the right to make some product. the sort of longer way to kind of think through it is that, you know, you get 0 divided by, well, I guess 4 squared gives you 0. So yeah, Q is smaller than K, which is a shift to the right. But when something is 0, you gotta shift to that side. So we're going to lose X amount of hydrogen and X amount of fluorine. And if we look at the stoichiometry of this reaction, for every one of either reactant, you gain 2 products. So with row C, remember the plus or minus depends on the shift. The side it's shifting to will be the pluses. The side it's shifting away from will be the minuses. But the value of x or 2x or 3x, whatever, easiest thing to do there is just pull it straight from the coefficient. Coefficient of 1 is x. Coefficient of 2, 2x. So again, the value of x comes from the coefficients, or value factor of x, magnitude, whatever you want to talk about. Plus or minus, that depends on the shift. Yeah. Whichever side it shifts to, that's the plus. Away from is the negative. So row E, we're basically adding the previous 2 rows together. So 0 plus 2x gives you 2x. 4 minus x is 4 minus x. Be a little lazy and leave off the 0.0 for space. And our equilibrium constant, whatever it is, although I'll give it to you there, Donna, is going to equal the concentration of product squared, because it's a coefficient of 2, divided by the concentration of each reactant. So plugging in what we know the value of K is 355. We know HF's concentration is going to be 2x. So we're going to square that. I can't write x's today. Concentration of each reactant is going to be 4 minus x. Or it'll be, you know, since they're the same concentrations, 4 minus x squared. All right, so this is where people start to try approximations, which really isn't going to work here because the value of K just is too close to your initial concentrations. When your concentrations and your K are that close together, approximation is not going to work. And if you try it, you'll see the 5% rule, which we talk about in class, is going to fail. But even in that case, you really don't have to worry about approximation or quadratics because, you know, notice that on the right side, we have a square on top, square on the bottom. So if we square this whole thing, square root of 355 is 18.8. Square on the top of the mountain gets rid of the square. And now it's a little bit easier to solve for x without having to worry about quadratics or FOIL methods or all the other stuff you were taught in math. So I won't show you every little step, but at some point you get to this point, 75.4 minus 18.8, x equals 2x. Actually, I guess I am showing you every step. Oh well, that's okay. And so you just keep solving away until you eventually get x equal 3.63. Which, now that we know what x is, we go back and revisit row E. So it means that our 2 reactant concentrations are going to be 4 minus x, which is 3.77. And so give me a little room here. And let's see, what's HF according to row E is 2x, and that'll give you 7.25. And don't forget, there's an easy way to check your work. If these are the concentrations at equilibrium, if we plug these back into our expression for K, we should get, pen, won't work. There we go. Plug it back into our expression for K, we should get something pretty close to the K that was given. So we got 7.25 squared over 0.377 times 0.377, 0. I guess I don't need the 0 there, but oh well. And that gives you, what, I get 370, which is reasonably close to the given K. It's a little off due to rounding, but you know, when you're wrong, you know it. You're usually a lot further off by 15, usually off by a factor of 15. So yeah, remember when you're doing all this equilibrium and quadratic stuff, and again, if you want to see more written out examples of that, for now you can go to the old Gen Chem Concepts page. I should have thought of, oh, actually it's General Chemistry Concepts is the official title. I was about to say I should have thought of a better title that wasn't such a tongue twister, but maybe I shouldn't try to shorthand it. Also, I shouldn't try to talk for 30 straight minutes without drinking some water. Good gosh. Actually 40 because I screwed up at the beginning. But yeah, I mean, a lot of times students will do the full method of the quadratic, or because they think it'll give them a more accurate answer. Yeah, maybe, but not enough for you to take all the time to do that crap. So again, don't forget about the other common thing you run into at this part of the semester as far as trying to find equilibrium concentrations. Those are the two main ways. One is, a quadratic that you may or may not be able to approximate away. But, don't forget about the other case where you can, if you got a square on the top and a square on the bottom, just do the square root trick. Right? It's works really well enough. All right, so that's it for now. I got nothing cute to say at the end anymore. I'm starting to give up on doing that. It's just too much work. To try to be cute and do this, it just isn't worth it. So that's it for now. I'm not doing one next week because it's our spring break and I'm tired. Although I'm going to have to work because for us, they're work days. They're not breaks. Such is life in Moscow. All right, but anyway, I'll be back in a couple of weeks, or if you're watching this in a later semester, it's already ready. Go watch it, unless something horrible's happened to me. Then I'm not going to do episode 9. That was it, 8 episodes. God, how weird would it be if something horrible happened to me now? And nobody would know because I'd just be saying, well, you might know if you're having a class now, but hopefully I'll see you next week. Anyway, bye.